Hello, my name is Scott Landau, and this is the Physics 2211 lab report on the motion energy changes of an oscillating mass. I'll begin by introducing some key ideas, relevant formulas, and diagrams. We'll then analyze the motion of the mass using Becker to construct a computational model to predict its motion. Finally, I'll analyze the results from the model, my observed data, and answer some key questions of the lab. Few key ideas in this lab include Newton's second law and the momentum principle. These are used iteratively to predict the motion of a mass utilizing net force. The net force is composed of gravitational force and spring force. The energy principle is also applied to calculate the total change in energy at any point. This total change includes change in kinetic energy, gravitational potential energy, and spring potential energy. Next, the velocity and position update formulas are used to model the change of the ball's motion. To do this, the net force is found through adding the spring and gravitation forces. The change in each type of energy is also calculated using the formulas displayed in this lab. I selected the system to be the mass, spring, and earth, so the earth does no work on the ball because it is in the system. Displayed here are two free body diagrams to illustrate the motion in the experiment. Force due to gravity always points down, and spring force always points parallel to the orientation of the spring. As seen in the diagrams, a compressed spring will make a force opposite to the attachment point, and a stretched spring will make force toward the attachment point. Using the video provided in tracker technology, I plotted the x and y positions of the mass for each frame of motion. It shows the x-axis to be to the right and the positive y-axis to be upwards. Here's an excerpt from my computational model. As seen, I first set the mass of the ball and its initial position and velocity vectors. I then defined g and found spring constant by utilizing the period of oscillation in the y direction, as well as the relaxed length of the spring. Finally, I calculated the energies of the system by using formulas previously elaborated on. In the main while loop, I calculated the force due to gravity and spring force in order to find the net force using the previous formulas. I then applied the momentum principle to update the mass's position and velocity, then updated L and L hat to readjust calculations. Finally, I calculated the change in each form of energy using the same method from the previous excerpts. Shown here is a graph computed from the model that displays the change in energy versus time. Gravitational potential energy, spring potential energy, and kinetic energy oscillate back and forth throughout the entire process. However, the amplitude of the kinetic energy is much smaller than the potential energies. The orange line on this graph is the change in total energy, which is zero throughout the entire procedure. In the x position and y position graphs, the predicted and observed motion line up pretty much accurately. However, the two lines deviate when reaching the positive peak of position in the x direction. This could be a result of calculating the spring constant using that y data rather than the x data, resulting in inconsistency in the data. The y maximum points deviate slightly as well, which could be a possible result of over-predicting the initial displacement in the y direction, which in turn adjusts all displacements after this one. A likely cause of this was the low frame rate and quality of the video that was recorded. Thus, a solution to this problem would be a higher quality and smoother video. Is the energy principle satisfied? As seen on the graphs, change in energy is equal to zero. Thus, the energy principle is satisfied because we stated earlier that the system is expected to have no change in energy since the Earth is included in the system. The differences in observed versus predicted x data could be solved by calculating time period for oscillation in the x direction and using this value to find the spring constant. The two oscillation times were calculated to display that they differ and would cause a variance in the spring constant calculations. This constant is used to predict the mass's motion as well as calculate the spring potential energy. A possible solution to this problem is to use the average of the two periods in the computational model. As seen in this display, the x position period results in 1.6383 seconds, and the y position period results in 1.5194 seconds. So in order to find the average, we would add them and divide by 2. And the formulas below that are how we calculate for the period in this situation. Thank you for listening to my lab report.